we're in college algebra, June 24th. And I'm just going to reshare again the thought for the week so we can have it on the recording for those who would like to see it again. So once again, accept responsibility for your life. Know that it is you who will get you where you want to go and no one else. All right. Let that sink in for a bit. And let's get into the lesson for today. Do we have any questions before we get started? Do we have any questions before we get started?
Yeah, I have a question about test 3.
Yes, sir.
So it's going to cover up to, sorry, just give me 1 second, up to rational functions?
Yes.
Stopping? Okay, thanks.
And we'll be covering rational functions today. So we'll be covering zeros of polynomials and also rational functions today. And if time allows, we'll get started on exponential functions. Then next week, we'll be completing exponential and logarithmic functions and linear and nonlinear systems next week. And then the final exam will be, well, next week will be test 4. You recall that test 4 will not be due till Sunday, July 5th. Because the Saturday is Independence Day. All right, just 1 minute here. All right, so according to the syllabus, we are still a day behind, maybe a little bit more than a day behind. Today is the 24th. We are supposed to be starting exponential and logarithmic functions today. So we are 1 class session behind. Today, we're going to talk about zeros of a polynomial and graphs of, well, and rational functions. Now, the dividing polynomials, you need to watch the video I have up on Blackboard that discusses that. That is actually a review of intermediate algebra. So you should have already covered that content in your intermediate algebra course. So if you go to course materials, as I'm doing here, and you go to the section that says video lessons, and you scroll down a bit, you will see a video lesson on dividing polynomials. It is in section 3.2 on it indicates a section 3.2, and it is one hour long. It's a 1 hour video lesson, okay? And of course, the corresponding notes are in the folder, the other additional folder, which is course materials, course notes, and the notes corresponding to that. It goes through the whole process of dividing polynomials, including long division with a number of examples, and then synthetic division with a number of additional examples. In addition to that, you can go to the bottom of the page where on the green bar, the bottom of the green bar, it says intermediate algebra materials. You click on that, and if you go to my class notes from spring 2019, there's a section about dividing polynomials. Where is that? exponent rules, scientific notation, polynomials, addition, subtraction, multiplication, division. Those are notes I did in class with students, so it's pretty extensive. And if you scroll down toward the bottom, you will see it talking about dividing polynomials with additional examples. 1, 2, 3, 4. 4 examples there, and a number of examples speaking about synthetic division. Okay, so those are resources for you to review about the dividing polynomials. All right, so once again, for there are a couple of people who need to contact me about the test, because I really need to get those out of the way so that other people can get to see their test, review their test. I have to get that complete, the test situation fixed before I can open up the test review for people to be able to see what they did that they had issues with. I also want everyone to make sure that you are, that you have are doing your Khan Academy assignments. If you're not doing your Khan Academy assignments, then you're putting yourself at a significant disadvantage. Khan Academy is worth 100 points. And I was told by someone, one of the students in tutoring, that in Khan, that the tutors don't always help with Khan Academy. Sometimes they are instructed not to do Khan Academy assignments with students. So you might have a little issue there. If you have an issue with that, here is something that you can do.
Professor, I have a question.
Yes.
So my computer is like the keyboard is in Portuguese, and so sometimes I have a hard time when I put the answers for like the signs. So like I just sent to the group chat an example of just a question of an answer that I answered like in the last test, but my computer, I didn't find the one of those signs. I don't know how you call it in English. And so I had a hard time, and I think like 2 or 3 answers were like wrong because I was just not able to find the sign on the computer. So my question is there a possibility, like when we're writing the answers, for us to have like some kind of keyboard inside like the website, so we can just click on it to make sure that like our answer is like exactly
your keyboard is in Portuguese, as in the keyboard keys that you're working on?
Yeah. Like my computer, I got it like somewhere else, and so like sometimes it's hard to match the symbols and the signs. So that's the thing.
But does it have the normal QWERTY keyboard with the regular letters? Because English and Portuguese use the same letters.
No. The letters is fine. I'm just saying that the signs, sometimes it's hard to find it. So like for example, the parentheses is fine, I can find those, but the one that is like the one that looks like a long I or whatever, I don't know, the one that is right next to the 2, I just sent an example. I don't know how you call that.
That's sign. Okay.
Yeah, for example, that one I couldn't find it last time, and I think 2 or 3 questions were like me like writing that, and I couldn't like find it. So maybe I was wrong with my answer, but I just want to make sure that whatever I write in my sheet is
with your answer, because all the answers that I require are using symbols on the regular keyboard, regular punctuation, and apart from that, brackets and parentheses.
No,
with brackets and parentheses, and there's no. I think I know what you're referring to. I'm going to bring up your thing here. I don't know if you can see it on the screen. That symbol there is over the bracket on the keyboard. Sorry, not over the bracket, over the backward slash next to the bracket. That symbol there, I don't recall giving any question that required you to write that as an answer, as part of an answer. That symbol between the 2 and the x?
Let me see. Yeah.
Yeah, so that symbol between the 2 and the x, which is it means such that in mathematics.
Right. Yeah.
I didn't ask any questions that required you to put that answer. My answers for intervals were always in interval notation. There's no infinity sign. Well, how did you get the infinity sign, Junior? All right, Haley, I see what you said there. They said they don't like, oh, you mean you can't? Yeah, there's no infinity sign, Junior. That's why on the test, I say for infinity, you simply type INF. INF, that. When you type INF, I will, I've set up the answer keys to check for INF in place of the word infinity or in place of the infinity sign. And I say that in the question, that you should use INF in place of infinity. That's correct, Matthew. Negative infinity would be the negative with the INF. And I'm still reviewing all the free response of the tests. So some of you, your answer, your scores may go up after I review the free response to see if there's any variation from the answer choice that I put. When I create a free response question, I have to put as many variations of the answer as I can, and sometimes that takes a while, which is sometimes why some of my tests take a little time to go up. So once everyone finishes the test, you're going to review them, so our grades might change. Yes, and I'm going to be reviewing some of the tests. I have not reviewed all of them already. I have to review the test, and I have to also review the videos for the lockdown browser to make sure there's no issue. That takes a lot of time. So I'm not just here chilling. I'm actually reviewing a lot of assessments. But again, please remember to do your Khan Academy assignments, okay? If you need any more clarification, Veronica, you can contact me afterwards. Hopefully I'll be able to resolve all of the test taking issues from the first two tests by later today, so you will be able to contact me if there's any issue. For those
Thank you.
No problem. For those who need to reach me, my cell phone number just type my cell phone number so that you'll be able to reach me via cell phone. 954-593-5749. All right, let's get into the work for today. Do we have any other questions, by the way, before I get started with the lesson? All right, so today's topic, zeros of a polynomial. This first topic, the first hour or so will be about zeros of a polynomial. The next half hour after that will be on rational functions. And then the rest of the class session will be on exponential and logarithmic functions. Excuse me. We will not be having exponential and logarithmic functions on the next test. The next test will go up to rational functions. All right. And again, please make sure you're doing your Khan Academy assignments. It won't cover all the topics here, but it will cover a good chunk, especially on quadratic functions. There are a lot of Khan Academy assignments on quadratic functions. All right, so zeros of a polynomial. Zeros just means x-intercepts. Actually, it means more than that. It means complex or real numbers that when you plug them in for x, you get 0 for the y value. So when those zeros are real numbers, they correspond to x-intercepts, like we covered last class. For example, negative, and this graph on the left side here, -1, 2, and 4 complex number, real numbers, okay? In this graph on the right-hand side, you have 3 real number intercepts, but you also have some complex number intercepts. By the way, what would be the multiplicity of the number -1 on the left side? Would it be an odd or even multiplicity? Number -1 on the left graph. Even, that's correct. What about 2? Odd is correct. And what about 4? Even again. Oh, sorry, odd again. That's correct. So the odd for, so Julian, you're correct. Minus, I hope you see why this one is odd. Whenever they cross the x-axis, that's an odd root. Sorry, that's a real number root or real 0, and the multiplicity is odd. In this case, the multiplicity at 2 is greater than the multiplicity at 4. And of course, -1 there. Today we're going to talk about how do we find real zeros of a polynomial function, and then we're going to talk about complex zeros of a polynomial function. The real zeros of a polynomial function will be based on, I think, 4 processes, 4 approaches. The first one is about the remainder theorem, which is a nice simple theorem that says, suppose you have a polynomial and you divide it by some expression, x minus c. The expression in particular is a linear expression where the coefficient of x is 1. So you're dividing the polynomial f of x by x minus c. Valentina, you need to review the notes and the video from the last class because we went through this quite a bit. When the zero of a polynomial is even, the graph touches the x-axis. When the zero of a polynomial is odd, it crosses the x-axis. Review the notes from last class for more details. So the remainder theorem says, if you want to find the remainder when you divide a polynomial by a linear factor of this form, x minus c, it's the same as just plugging in c into the function. All right? So if I have f of x equal to 2x cubed minus 3x squared plus 2x minus 1, and I want to find the remainder when x is divided by x plus 2, when f of x is divided by x plus 2, all you have to do is plug in -2 into the function, and that will give you the remainder. Now, if I were to do synthetic division, as you should have covered in intermediate algebra, you would drop the coefficients down, 2, -3, 2, -1. Make sure no coefficients are skipped. If there's a term that's missing, you put 0 in its place. Then you drop the first coefficient downward, then you multiply this -2 out here by this 2. Now the question is, where do I get this -2 out here? I take the linear factor, set it equal to 0 and solve for x. And that is how I got the -2. So I take x plus 2, set it equal to 0, solve for x, again, x equal to -2. That's what goes here. And that would represent the possible 0. And remember, x plus 2 is the same as x minus -2. So that's another way of thinking of getting this -2 here. The linear factor here is something that was arbitrarily chosen. So for this example, we want to find the remainder when you divide this polynomial by this linear factor, x plus 2. And I could have used a different linear factor. So now I use x plus 2. Going through synthetic division, I put all the coefficients down, drop the first coefficient, multiply this number by this number, I get this number. Then I add these two numbers, I get -7. Then I multiply -2 by -7, I get 14. Then I add those two numbers, I get 16. Then I multiply -2 by 16, I get -32. Then I add those two numbers, I get -33. And that's the last number. That number will be the remainder. However, if I just take this expression, and if I just take this -2 and plug it into the function, I would still get -33. So a shortcut for finding the remainder, instead of doing a whole long process of division, I simply plug c into the polynomial and see what the remainder is, and see what the answer is. So if the remainder is not 0, then this x plus 2 is not a factor. That linear expression is not a factor. Because when you have a factor, the remainder should be 0. A factor should divide perfectly into the polynomial. So we see then that x plus 2 is not a factor of this expression, because when you divide by x plus 2, you do not get 0. And therefore, -2 is not a 0 of the polynomial, because when you plug in -2, you do not get 0. So the answer we get from the division is the same answer we get if we plug in -2. Now, the factor theorem is a corollary of the remainder theorem, which says if when you do the division by x minus c, if your remainder is 0, then x minus c is a factor. And of course, again, that's simply by just plugging in c into the function. So if f of c is equal to 0, then x minus c is a factor, and if x minus c is a factor, then f of c is equal to 0. That's what if and only if means. It works both ways. So the question is x plus 3 a factor of this expression? Right away I know it's not. I'll tell you why in a few minutes. But what we can do is check. We just plug in -3 into the function, and the answer comes out to be 161. And since the f of -3 is 161, then we know that x plus 3 is not a factor of this expression. All right. All right, let's try another one. Let's see if another number works. Let's see if, I don't know if any other works. Does -2 work? Yeah, I believe 2 might work, or never. 2 might work. Let's see if 2 works. So let's plug in 2 into this polynomial. -4 times 8 is 32. -32. And then -32 plus 8 is -24. Yeah, -2 doesn't work. Apparently nothing works in this polynomial. No rational number works, at least. All right. So the goal of this section is to learn how we can factor higher polynomials and thereby identify the real and the complex zeros. The first rule is the Descartes rule of signs. And Descartes rule of signs is helps us to get to a certain place where we can figure out the how many roots of a certain type. It's made from, the name is from the person who came up with it, his name is René Descartes. It's spelled D-E-S-C-A-R-T-E-S because he was French. He's the one who came up with the Cartesian coordinate system. He was a philosopher that used mathematics. All right. So he was also a mathematician, but his primary focus was philosophy. And mathematics is actually a branch of philosophy, at least initially. And he came up with the Cartesian coordinate system, what we call the XY plane. And then he also did a lot of mathematical elements. He also came up with this statement that you've heard, I think, therefore I am. He wrote a book called Meditations about existence. And that's where that statement, I think, therefore I am, comes from. So he came up with a rule called Descartes' rule of signs. And it's very, well, not very simple. It takes a little time to remember. There are 2 parts to it. The first part says, how many times do you have a change in sign from one term to the next? For example, the first term here is a positive. The next term is a positive. So there's no change in sign from first term to second term. But from second term to third term, you're going from a positive to a negative. So that's 1 change in sign. From third term to fourth term, there's no change in signs, but you're going from negative to negative. So we still have 1 change in sign so far. And then from this term, negative x to 2, we have another change in sign. So we have two sign changes, from positive 3 to negative 3x squared, and from negative x to positive 2. So when we have two sign changes, then that means we have either two positive roots or an even number less than that. In this case, we either have two positive roots or no positive roots, because an even number less than 2 would have to be 0 or a negative, and we can't have a negative number of anything. So Descartes' rule of sign says if you look at how many sign changes you have, that will tell you how many positive roots you'll have, or an estimate of how many positive roots. In this case, either you have that number of positive roots or an even number less. In this case, even we have 2 positive roots or 0 positive roots. Then the second part says is if you replace all your x's with negative x, and then you do all the sign changes again, that will tell you how many negative roots you have in the same way. So let's start off with the positive roots. We have 2 sign changes here. Since we have 2 sign changes, that means we'll either have 2 positive roots or 0 positive roots. And these must be real numbers. But when we do f of negative x, our sign changes, let me just back up here. So we do f of negative x by replacing all the x's with negative x and simplifying. And then we have 2 sign changes again. So again, we have 2 sign changes. So we either have 2 negative real roots or 0 negative real roots. So when we did it without the sign changes, we had 2 sign changes with it when you had positive. And when you replace it with the negative x, you have two sign changes again, which means we'll have either 2 positive zeros or none, and in this case, we'll have 2 negative zeros or none. And so we can now check. Well, it turns out that doesn't tell us what the zeros could possibly be. It just tells us what numbers we could try. I can give you an example now. If I plug in 1 into this polynomial, I get 1 plus 1 minus 3 minus 1 plus 2. That gives me 0, which means 1 is a positive 0. That means since I have at least 1 positive 0, I must have 2, because Descartes' rule of sign says I need to have 2 real zeros or none. I know it's not none because I have at least one of them, 2 positive real zeros. So when I plug in 1, I got 0. So there should be another positive real 0 somewhere. All right. And what I'm going to do is switch over to Desmos. And I'm going to put this function in on Desmos so you can see what it looks like. X to the power 4 plus x3 cubed minus 3x squared minus x plus 2. And as you can see, what did I do wrong here? All right, so here's the issue I have. So at 1, the graph bounces off the x-axis, which means 1 has a multiplicity, an even multiplicity, which means it's a positive root twice. So it doesn't talk about whether they're positive different roots. How do we use Desmos during the test? Will the lockdown browser let us? When I create the test, Madison, I always put a link to Desmos on the test instructions and on the test description. Has anyone tried to open Desmos while doing the test? If you have, just text in the box. I tested it and it worked for me when I was testing it. And I want to know if it worked for other people. All right, Jillian says it works. Thank you very much, Jillian. Now, if you notice here, so we have a repeated 0 at 1 right here. And then we have, that's 1 positive 0. And then we have 2 negative zeros, -2 and -1. As Descartes' rule of sign said, 2 negative real numbers and actually one positive real zero that is repeated, so it's there twice. Yeah, I set it up so that you can click on it, and what it does, it opens in a new tab, so you will not be leaving your test. The lockdown browser just allows you to have those. Now it only works because I set it up that way. The lockdown browser allows me as the instructor to set up specific links to specific web pages or web links, email specific links online. And I have to go through a little process to allow certain domains and so on. So if it's there as a link, you can click on it and it will open in a new page and you can access it, okay? And that's why it works. It won't work for anything else. You can't actually go to any other page except for the ones I specify. All right, so continuing here. Now, the next thing we want to look at is, well, this is just an example. How many sign changes do we have here? F of x equals to negative 3x to the 5 plus 4x to the 4 plus 2. We have 1, which means this graph must cross the x-axis one place because you can only have one positive 0. And of course, that is expected because the degree is 5, which means, and the leading coefficient is negative 3. That means it starts above and ends below. As x goes to negative infinity, the graph goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. Since it's telling you you must have one or an even number less of positive zeros, you must have one because you can't have a negative number of positive zeros. All right? So since there's only one sign change, there must be only one positive real number 0. Now when we replace x with negative x, we get no sign changes. So we won't have any negative zeros. You only have a positive 0. Okay? So as a result, we'll only have one positive real number 0 and no negative real number 0. And later on, we'll find out that the other zeros will therefore be complex zeros. So let me show you what the graph looks like now. So f of x equal to negative 3x to the 5 plus 4x to the 4 plus 2. And there you have it. If you look at this graph here, it crosses the x-axis somewhere right here, which is an approximate value. It's pretty hard to identify. 1.474, which is that you have to use something called the Newton method, which is using something called the intermediate value theorem to figure an estimate of this point. Now back to the original equation, we want to find out the factors, and this is a big theorem that is going to help us. And that's how I could know which factors to try, and now I knew that in the other question, the factor we tried didn't work. If you have a polynomial with integer coefficients, that means all the coefficients are integers, positive or negative whole numbers, or 0. All right, and you want to find out all the possible rational number zeros. That means all the possible zeros that are rational numbers. Rational numbers are real numbers that can be written as a fraction of 2 integers. If you want to find out all the possible rational number zeros, what you do is you take the constant term, and if there's no constant term, then the constant term is 0. You take the constant term and find all the factors of the constant term. And you take the leading coefficient and find all the factors of the leading coefficient. And then you find all the quotients of the factors of the constant over the factors of the leading term, positive and negative. those will be the possible rational zeros. So this is how it says here, that f be a polynomial function of degree 1 or higher. If we have it in this form where all of these numbers are the coefficients, and there's at least one of them that's not 0, then if P over Q in lowest terms is a rational 0 of f, then P must be a factor of A, 0, and Q must be a factor of AN. That means if you take a rational 0, simplify it to its lowest terms, then the numerator must be a factor of the constant, and the denominator must be a factor of the leading coefficient. So here's an example. What are the possible factors of 2? That's correct. 1 and 2 are the factors of 2. And of course, what's the possible factors of the leading coefficient here, which is 1? Just the number 1, that's correct. So then what we do is we just write down the factors of 2 and the factors of 1 and divide all the factors of 2 by the factors of 1. And then we put plus or minus, so it could be positive or negative. So the answer here would be positive 1 over 1 or negative 1 over 1, positive 2 over 1 or negative 2 over 1. So that we end up with 2 possible factors here, positive or negative 1 or positive or negative 2. That's what I have right here. Positive or negative 1, positive or negative 2. No, that's 4 possible factors, not 2. 4 possible factors, so I can try them out. And remember that a factor could have a multiplicity that's bigger than 1. That means a number could be a factor multiple times. That's also allowed. So we start by plugging in. We start by plugging in 1. When we try 1, we plug in 1 into the function, we get 0 as the remainder, which tells me that 1 is a factor of this, x minus 1 is a factor of this polynomial. So I divide this polynomial by x minus 1, and we get x cubed plus 2x squared minus x minus 2. All right? So that's what this polynomial then can be written in as x minus 1 times x cubed plus 2x squared minus x minus 2. I got this part from this. These are the coefficients of the quotient, which is always 1 degree less than the coefficient of the dividend, the thing you're dividing into. Now, again, I'm going to try again to see if 1 is a factor, because again, these same 4 numbers could be factors of this plus or minus 2, this minus 2. So I'm going to try 1 again. Descartes' root of signs tells me from before that I should have 2 positive and 2 negative. In this case, Descartes' rule of sign says there's another positive, because there's only 1 sign change. Okay, so I take this piece and I plug in 1 again, and it turns out to be 0, which tells me that 1 is another factor again. 1 is a factor again. So I do the synthetic division and I get this, x squared plus 3x plus 2, which tells me then that this expression is x minus 1 times x minus 1 times x squared plus 3x plus 2. And then, of course, x squared plus 3x plus 2 is a quadratic expression, which factors very nicely. And so this whole thing factors out to be x minus 1 times x minus 1 times x plus 2 times x plus 2, or x minus 1 squared times x plus 2 plus times x plus 1. And that, we drew this graph on Desmos, that matches our graph. We have n behavior because the leading coefficient is positive and it's an even degree polynomial. The graph goes up at both ends. The graph has intercepts at, the y-intercept is 2, x-intercepts are -2, -1, and 1. multiplicity of 1 at the negative intercepts and a multiplicity of 2 at 1. So the graph looks like this. Do we have any questions about that? Now, the Descartes rule of signs only gives us rational zeros. It doesn't give us all possible real zeros. It only gives us rational zeros, only zeros that are rational numbers. So it won't give us all the possible zeros that we're looking for, only certain types. Now, in this case, what are the possible zeros that we can have? We will have to find all the factors of 9 and the factors of 2. What are the factors of 9? 1, 3, and 9. Correct. What are the factors of 2? 1 and 2. So the possible zeros would be plus or minus 1, 3, or 9 divided by 1 or 2. That means we'll do 1 over 1, 3 over 1, sorry, 1 over 1, 1 over 2, 3 over 1, 3 over 2, 9 over 1, 9 over 2, and all of those plus or minus. We're talking about 12 different possible factors here, which means we have to do a little extra analysis. Now, if you look at this expression, you realize that there's no sign change. No change from positive. They're all positive, which means there is no positive zero to this for this polynomial, which allows me now to say, wait, no positive zeros. I only have to check negative numbers. So then my rational zeros are only possibly negative 1, negative half, negative 3, negative 3 over 2, negative 9, and negative 9 over 2. Now, if I replace all my x's with negative x, there will be a sign change from here to here, sign change from here to here, sign change from here to here, and sign change from here to here. So I'll have 4 negative roots. That's if I replace all my x's with negative x. So I can start off by trying negative 1. And guess what? When I try negative 1, I plug in negative 1 into the expression. I get 2 minus 13 plus 29 minus 27 plus 9. That gives me 0, which means negative 1 is a factor. Which means negative 1 is a 0. It's a value of x that makes the function equal to 0. That means when you divide this expression by x plus 1, you'll get 0 remainder. And this is the quotient. So this expression could be written as x plus 1 times 2x to the 3 plus 11x squared plus 18x plus 9. And then we're going to try dividing by negative 1 again, because there's no reason not to try. We do it again, and we get another factor. X plus 1 is a factor twice. And now this is 2x squared plus 9x plus 9, which we can factor as 2x plus 3 times x plus 3. So this expression here can now be written as x plus 1 squared times x plus 3 times 2x plus 3. And therefore we have our 4 factors. One of them is repeated. So we have negative 1, negative 3 over 2, and negative 3. And that's the graph. Y-intercept is at 9. Now, as I said, the rational zeros theorem only allows us to find rational zeros, not all real numbers. It doesn't allow us to find irrational numbers. And for irrational numbers, you might have to estimate. So let's say we're trying to solve this equation here. And what I'm going to do is I'm going to switch over to Desmos. I'm going to plot that equation. Now, as you can see on my graph here, the graph only crosses at one place, and it does not cross at a nice number either. Well, this one does cross at 5/2. Yeah, it does cross exactly at 5/2 one time, because there's actually one sign change, positive to negative one time. And there's no zeros, because if I change all my x's to negative x, there is no sign change. Actually, there is one sign change. Sorry about that. Let me just check to make sure. Checking again. If I change all my x's to negative x, I get a negative, and a positive, and a negative. Oh, I either get two negative zeros or none, and this turns out to be none. So this one won't work as nicely as I want to, but it will be sufficient. So this does have a rational zero at 5/2. All right. Dakar's rule of sign says we have one sign change, so we have one real zero. We try all of our possible numbers. We try 1, -1 doesn't work. 5 and -5 doesn't work. Half and -half don't work. 5/2 does work. So when you try, it's pretty simple. You don't have to do the long division. Just plug in the number into the polynomial, and if you get 0, it's a factor. If you don't get 0, it's not a factor. So if you plug in 1, you'll get -9, not a factor. Plug in -1, doesn't work. Plug in 5, it doesn't work. Plug in a bunch of different numbers don't work. But here's something that's interesting. When I plugged in 1, I got a negative answer. And when I plugged in 5, I got a positive answer, which means this graph crosses the x-axis somewhere between 1 and 5. So I'm going to try a number between 1 and 5. We can try 5/2. Turns out when I try 5/2, it works. But here's the thing. The intermediate value theorem says that if you have a continuous function and you plug in two different numbers, one of them gives you a positive answer and the other gives me a negative answer, then the graph crosses the x-axis between those two numbers. That is what the intermediate value theorem says. There's a value in between two numbers that the value takes every possible y value between two numbers if the function is continuous. In particular, if you have a continuous function and you plug in an x value and you get a positive answer, and you plug in another x value and you get a negative answer, then that means the graph crosses the x-axis between those two numbers. In this case, when we plugged in 1, we got a -9. When we plugged in 5, we got a positive 155. That means this graph crosses the x-axis between 1 and 5. It doesn't mean it has to cross at a rational number. It may cross at an irrational number, but it will cross somewhere. So that's what the intermediate value theorem says. Let f denote a polynomial function, and if a is less than b and f of a and f of b have opposite signs, then there's at least one 0 between a and b. And all we have to do is just try numbers in between them until we get our result. Now, again, we already checked on the Desmos calculator, and we saw the graph, and we could tell immediately from the graph what the x estimate is. But this is how it's one of the ways to do it. All right, so for this question here, we try -1, it doesn't work. We try 0, and it gives you +2. So we know that this graph crosses the x-axis somewhere between -1 and 0. Because when we plug in -1, we get -6. And when we plug in 0, we get 2. And this is a polynomial, which means it's continuous. Polynomials are smooth and continuous. Smooth and continuous for all real numbers. Pardon me. So I'm going to try, I try -1, I get -6. When I try 2, when I try 0, I get 2. So then I choose a number between -1 and 0, say half, -half. When I plug in -half, I get a positive answer, which means the graph now crosses between -1 and +half. So now I'm going to try a number between -1 and +half. So I try -0.7. When I plug in -0.7 into the function, I get a negative answer. So that means the graph crosses between -0.7 and -0.5. Graph crosses between here. So I try a number between those. -0.6. When I try -0.6, I get a positive answer. Where does the sign change? Does it change between -0.7 and -0.6 or between -0.6 and -0.5? When you plug in -0.6, you get a positive. When you plug in a -0.5, you get a positive. So there's no sign change between those two, but there's a sign change between -0.7 and -0.6, which means the graph crosses between -0.7 and -0.6. So I try a number between -0.6 and -0.7. And so I just keep going and doing that over and over until I get an answer. Now let's take a look at what it looks like on Desmos. So I go x to the power 4 plus 8x cubed minus x squared plus 2. And as you can see, let me just magnify that a bit. As I keep going, it's approximately -0.6046. That's what it comes down to, -0.6046. That is an approximate value. It's not the exact 0, that's an approximate value. In fact, if I plug in -0.6046, it won't give me exactly what I'm looking for. See, it doesn't give me exactly what I'm looking for. It gives me a close number to 0, only precise up to 4 decimal places, but it's not an exact answer. It won't give me 0. And if I put a 1 here, uh-oh. Yeah, I accidentally pressed the X, so unfortunately, okay, there we go. This now is now precise up to 4 decimal places. Again, but you get the idea. All right. Do we have any questions before I go on to some examples? All right, before I do the examples, I'm just going to do the complex zeros, and then we're going to do a bunch of examples to wrap everything together. In the video on Blackboard, I do examples about the rational zeros and the Descartes rule of science questions. And I think I did something with the intermediate algebra, intermediate value theorem. But for now, I'm going to do I do those examples before I go to complex numbers. But I'm just going to do the complex numbers here, and then we'll do the examples all in one batch. So here's the key about complex zeros. Complex zeros, if you have a polynomial and a number is a complex zero, its conjugate is also a complex zero. So here's an example of a complex, a polynomial with complex zeros. I have x squared plus 4 equals 0. There's no real number that works here. So I solve for x by setting x squared equal to negative 4 and then taking the square root of both sides. I get positive and negative 2i. Those are two complex numbers that are conjugates of each other. And if you recall, complex numbers are conjugates of each other if the imaginary part of one has the opposite sign as the imaginary part of the other one. In other words, if you have a complex number a plus bi, then its conjugate is a minus bi. Okay? A real number is its own complex conjugate, so that won't count. Here's another example here. I can solve this one by using quadratic formula, and I get negative 1 plus or minus 2i. Again, these are two complex numbers. They are conjugates of each other. Negative 1 plus 2i and negative 1 minus 2i. In general, whenever you have a complex solution, a complex zero for a polynomial, then its conjugate is also a zero of the polynomial. So this is what it says at the bottom here. It says, notice that with either type, the complex zeros come in conjugate pairs. There are two complex solutions that have the same real term and opposite signs on imaginary terms. This will always be the case. Complex zeros come in conjugate pairs. That is if the polynomial has real coefficients, which is the only type of polynomials we'll be dealing with. So these are the rules here. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. That means if it has degree 4, it will have 4 roots, not necessarily distinct. Some of the roots may be repeated. So let's say you have a root like 3, and 3 has multiplicity 5, and the polynomial is a degree 7 polynomial. Then you'll have 2 other roots somewhere. They could be the same number twice or 2 different numbers. In other words, you can count a root multiple times, and that counts. And then the next thing is if a plus bi is a polynomial equation where the b part is not 0, that means it's a complex number which is not real. So if a plus bi is a complex number that is not real and it's a root of a polynomial equation, then its conjugate is also a root. All right? So the fundamental theorem of algebra says if f of x is a polynomial of degree n and n is positive, then the equation f of x equal to 0 has at least one complex root. In other words, if you have any linear function or polynomial with degree 1 or higher, you must have at least one complex number's root, and that includes real numbers. All real numbers are complex numbers. And the number of roots, including with multiplicity, is indicated by the degree. If the degree is 5, you'll have 5 roots. Some of them may be the same root twice, or multiple times, but it still counts. So, if asked to find a polynomial that has zeros 2 and 1 minus 3i, then you know that 1 plus 3i must also be a root. So how do we find that? Well, if x equal to the root, then x minus the root is a factor. So that means x minus 2 is a factor, and x minus 1 minus 3i is a factor, and x minus 1 plus 3i is a factor. You can distribute this side here, distribute these, and see what you get. Then distribute these two here, and the i's will cancel. The i's will cancel. And then I squared will become negative 1, And then you have this little nice quadratic here. And then this can be just distributed to give you what you want. That's the polynomial in standard form. This polynomial, it has roots 2, 1 minus 3i, and 1 plus 3i, which you can always check using Descartes' rule of signs, which tells us we have 1, 2, 3 sign changes, which tells us we either have 1 positive 0 or none. And when we do the negatives, we get no sign changes, so there's no negative zeros. So when we check which, we use Descartes' rule, we use rational zeros theorem, and we see that you have a bunch of zeros to try, and you can check them out. All right, so we know that we only have positive zeros. When you plug in 2, you get 0, and that gives you this expression here, which you can solve that by quadratic formula. So that's just a way to check back. Here's one. You're given that a 0 is 3i. Find all the remaining zeros. How many zeros should this polynomial have? How many zeros should this polynomial have? Not one. The number of zeros is equal to the degree of the polynomial. So how many zeros should it have? 4. That is correct. Now, one of those zeros is 3i. So what's another zero that we know right away? Negative 3i. That is correct. So since we know that one of the zeros is negative 3i, which I'm not going to do the long division for this because that's painful. We just multiply negative 3i times, we just do x plus 3i times x minus 3i, and that gives you x squared plus 9. Then when you divide this polynomial by long division by x squared plus 9, you end up with 3x squared plus 5x minus 2, which then, with a combination of Descartes' rule of signs and rational zeros theorem, then we know that we should get a positive 0. 1 positive 0. So we try 1. Actually, you don't even have to do all of that work. Just do the quadratic formula with this, and then that will give you the answer. And the quadratic formula will give us 1/3 and negative 2. So the zeros are 3i, negative 3i, 1/3, and negative 2. All right, so that's our example there. All right, for this particular question, I'm going to show you the way I'm going to do it, that you may have to do it on the computer, on paper if you're doing it. You can do the long way, which could be tedious, or the way I'm going to show you, which could also be tedious. So we already know that so we know that x minus 3i and x plus 3i are factors of this polynomial. So when I multiply them out, I get x squared plus 3ix minus 3ix minus 9i squared, which gives us x squared plus 9, because these guys cancel and I squared is negative 1. And so therefore, I need to divide x squared plus 9 into 3x to the 4 plus 5x cubed plus 25x squared plus 14x minus 18, and that should give me a remainder of 0. Now, this is not synthetic division because this is not a linear factor anymore. So I do x squared into 3x to the 4, and that gives me 3x squared. Then I multiply by 3x squared. I'm going to multiply the 3x squared to each term and write them under the appropriate term. So 3x squared times 3x cubed is 3x to the 4. 3x squared times 9 is 9x squared. Oh, 27x squared. And then I'm going to subtract that from the term above, the expression above. And that will give me, these terms will cancel. That gives me 5x cubed minus 2x squared. And then the 14x's and the minus 18 are subtracting 0, so that's that. Then I do x squared into 5x cubed will give me positive 5x. Then I multiply 5x times each term again. So I end up with 5x times 5x squared is 5x cubed, and 5x times 9 is 45x. Again, I subtract it from the expression above, and that gives me negative 2x squared minus 14x minus 45x is negative 31x minus 9, and then minus 18. And then I do, let me make sure I didn't make an error here. Three times 9 is 27. Oh, that's a 45. Thank you very much. I was wondering why it's not computing. 45x. Thank you very much. I made an error in my transcription. Now, this part gives me 0. And then I do a division. I do a subtraction, sorry, another division. X squared into negative 2x squared is negative 2. You multiply. So we have negative 2x squared plus 9, plus 18. And you get 0 as a remainder. And then what this tells you is that this expression can be written as x squared plus 9 times 3x squared plus 5x minus 2. And this can be factored, or you can use a quadratic formula. Either way, well, if we factor this, we'll end up with 3x squared plus 5x minus 2. And to check if it can be factored, just do the discriminant. 25 minus 4 times negative 2 times 3. That's 25 plus 24, which is 49. And that means you have a perfect square, which means it can be factored. Multiply 3 times negative 2, get negative 6. You need two numbers that multiply to be negative 6 and add to be positive 5. Those numbers are positive 6 and negative 1. Which you then factor by grouping. And then you get 3x times x plus 2 minus 1 times x plus 2. And that gives us x plus 2 multiplied by 3x minus 1. And that's how we get f of x is equal to x squared plus 9 times x plus 2 times 3x minus 1. So my zeros are plus or negative, well, I'm going to write them this way. Negative 3i, positive 3i, negative 2, and positive 1/3. By the way, when I'm asking you for the zeros, the real number zeros, I want you to put them in order from least to greatest, from left to right. Okay? In particular, when I'm asking for those with multiplicities, I need you to put them in order from left to right on the test. Otherwise, it won't read properly and you will get the question wrong. when it's talking about complex zeros, just I will make adjustments to make sure I can read as many as possible. But for the sake of, for real zeros, you need to put them correctly. Do we have any questions?
Can you just leave this up for 1 second?
Okay. Give me a moment.
Got it, thanks.
Okay, good. Now, the books, of course, are up on Blackboard, and we're going to take a break in a few minutes and then come back and do some examples and then do rational functions, which is going to be a pretty short section of the course. Actually, the video is pretty long. So I don't know how short it's going to be, but we'll see. But the books, of course, are the OpenStax textbook, the Blitzer book that is posted on Blackboard, and the Sullivan book. If I do the OpenStax textbook, over on the left side here, there is a section on polynomial functions, chapter 5. And there's a section on zeros of polynomial functions, section 5.5. So there's a number of questions there that we can try. Okay. And I'm not gonna do the divisions, but you can do the remainder theorem to find the remainder. And then find all rational zeros, and complex zeros. So we're going to do a few of those when we come back from the break. And of course, you can also find answers in the Blitzer book under the section that says polynomial and rational functions. That's chapter 2. And the Sullivan book, polynomial and rational functions, is also chapter 5. When we come back, we'll take a look at some questions on the OpenStax textbook, and then we'll go into rational functions. Some people are having audio problems, so all right, if you're having audio problems, you can sign out and sign back in for those for future reference. At this time, we're going to take a 10-minute break, and we will resume at 9:37. Okay, we are now going to go into a few examples from the textbook, which is, I'm going to use the college algebra textbook from the OpenStax page. So that's the book we're going to be using today. You can, of course, do other questions from the other books. Because of time, I probably won't be able to do many examples, but let's start out with a few. So for the first set here, it's pretty straightforward. if you want to find out the remainder, if you're plugging in trying to find linear factors, you just plug in the number. Choose two of these and I'll do it quickly for you. From numbers 6 to 13, choose two of those questions and I'll do them. Number 9 and number 13. Oh, pardon me. All right, so number 9. I mean, these are extremely easy using the remainder theorem. All right, so for number 9, it's pretty simple. All you have to do is plug in this thing here. You set that equal to 0. And then solve for x. And then that x goes into these x's right here. Well, there's no x there. So we end up with -3 times x times 4 squared plus 6 times 4 plus 24. And that will give us -3 times 4 squared is -48 plus 48 is 0. So the remainder is 0. That's it. When you divide -3x squared plus 6x plus 24 by x minus 4, the remainder is 0. Doesn't tell you what the quotient is, but it does tell you that the remainder is 0. Do we have any questions about that? Next. For this one here, we take the x plus 2, set it equal to 0, and then solve for x, and we get x equal to -2. So what will be the remainder then when we divide 4x cubed plus 5x squared minus 2x plus 7 by x plus 2? What will be our remainder? Or we have an answer of 15, and we have an answer of -1. Let us check. 4 times -2 cubed plus 5 times -2 squared minus 2 times -2 plus 7. PEMDAS tells us to do exponents first, so 4 times -8 is -32. -2 squared is +4 times 5 is +20. -2 times -2 is +4. So we have -32 plus 20 plus 4 plus 7. That's equal to -1. So the remainder is -1. Any questions about this? Hussein, did you see where the error you made occurred? Okay, great. Now let's go on to the next set of questions. Next set of questions says, for the following exercises, use the factor theorem to find all zeros for the given polynomial function and one factor. So they give you one factor and they want you to find all the other zeros. So choose from that set which ones you'd like me to do. We have number 16, number 19. Those are the two I'm going to be doing, number 16 and number 19. Let me just prep the gentlemen, number 19 and number 16 look very similar in their approaches. So I'm going to ask for a different one. Let's try number 21 instead. So I switched out number 19 for number and put number 21 instead so that we can have a little bit of variety in our examples, okay? So the instructions are, you're given one factor, use the factor theorem to find the other factors, okay? Now what we're going to first do is verify that we're working with factors by just plugging in the number and verifying that that's what we have. All right, we're going to plug in f of negative. We're going to plug in, what did I just do? We're going to plug in -3 into the function here for number 16. We get 3 times -3 cubed plus the square of -3 minus 20 times -3 plus 12. Working that out, you get, this is -81 plus 9 plus 60 plus 12. 9 plus 60 is 69 plus 12 is 81. And so this gives me 0. Good. And then we're going to divide f of x by x plus 3 using synthetic division. Our coefficients are 3, 1, -20, and 12. And so what we do is we drop our first coefficient. We get 3, and we multiply -3 times 3 is positive, is -9, and then we add to the one above. And so we get -8. And then -3 times -8 is positive 24. And negative 20 plus 24 is 4. Negative 3 times 4 is negative 12. Negative 12 plus 12 plus negative 12 is 0, which we expect. So then that means we can write f of x as x plus 3 times 3x squared minus 8x plus 4. Do we have any questions so far? No questions. So the only thing we have to do now is factor this remaining expression, and we can factor this. You can check by doing the discriminant, and 64 minus 48 is 16, and that is factorable. So we can then say f of x is equal to x plus 3 times what we get when we factor 3x squared plus 8 minus 8x plus 4, which is two numbers that multiply to be 12 and add to be negative 8 are negative 6x and negative 2x. Well, negative 6 and negative 2. And then we just factor that. We get 3x times x minus 2 plus minus 2 times x minus 2. So we end up with f of x is equal to x plus 3 times x minus 2 times 3x minus 2. So that is f of x completely factored. Do we have any questions so far? So based on what I just did here, what are my zeros? What are all my real zeros of this polynomial? Negative 3, positive 2, and positive 2/3. That's correct. Do we have any other zeros? That's correct, because the fundamental theorem of algebra says that if your degree is 3, then you can have no more than 3 zeros. Counting repeated, you have exactly 3 zeros if you count the repeated ones as multiples. So it's negative 3, negative 2/3, positive 2/3, sorry, and positive 2 in order from least to greatest. All right, let's try the next question here, this one here. Now again, we're gonna solve for x, and I'm gonna call this f of x because of, so I'm gonna say f of x is equal to 2x cubed plus 5x squared minus 12x minus 30. And then what I'm going to do is I'm going to take this linear expression, 2x plus 5, set it equal to 0, solve for x. X is equal to negative 5/2. Now if I plug in negative 5/2 into this expression, I should get 0. So we have 2 times the cube of negative 5/2 plus 5 times the square of negative 5/2 minus 12 times negative 5/2 minus 30. Because I don't feel like doing it in my head, I'll do it on Desmos. 2 times negative 5/2 cubed plus 5 times negative 5/2 squared minus 12 times negative 5 halves minus 30. Answer is 0. There we go. So we know that it works. So let's now divide this expression by this one. Now this doesn't look like it will work, but what we could do is synthetic division. So we have let me show you something a little quickly here. If I do f of x divide by 2x plus 5, that would be the same as 2x cubed plus 5x squared minus 12x minus 30 divided by 2x plus 5. Are you with me so far? I don't want a number in front of the x, so I'm going to divide top and bottom by 2. So divide the numerator by 2 and the denominator by 2. So what that gives me is this expression here. X cubed plus 5 over 2x squared minus 6x minus 15 over x plus 5 halves. Someone saying you cannot see what I'm writing on the board. You might want to move my, is anyone else having difficulty seeing what I'm writing on the board? All right, so Vilner, you might need to sign out and sign back in. Haley, you're having difficulty seeing it? Is it too small? Oh, so you can see it. Okay, good. So what I did was I needed this linear factor to be so that the coefficient of x is 1. So what I did was I divided the numerator and denominator by 2 so that the coefficient of x squared is 1. And then I'm going to use this with this modified expression. So now with the long division, it's into the division here. My coefficients are not 2, 5, negative 12, and negative 30. My coefficients are 1, 5 over 2, negative 6, and negative 15. Okay, welcome back, Kaylin. So my number here is, of course, negative 5 over 2. Same as before, we drop the 1 and multiply by negative 5 over 2. We get negative 5 over 2. That gives me 0. Multiply by negative 6 multiplied by negative 5 over 2 would be 15. And then this would be my remainder. So that means this expression becomes x minus 6, x squared minus 6. So we can then say that this expression can be written as, let's see, x cubed plus 5 over 2 x squared minus 6x minus 15 is x plus 5 over 2 times x squared minus 6. Oh, times 2, because we have divided everything by 2. Let's see if this works. If I distribute here, we end up with x cubed minus 6x plus 5 over 2x squared minus 15. And then everything is multiplied by 2. That gives you 2x cubed plus 5x squared minus 12x minus 30. So it does work. So what are my zeros? Oh, by the way, x squared minus 6 factors ought to be something not too pleasant, but workable. X plus square root 6, x minus square root 6. All right, so my real zeros then work out to be what? What are my real zeros? Anybody? Negative radical 6, that's correct. Radical 6, negative 5 over 2, that's correct. All right, so let me just quickly review what I just did. First of all, this is a linear factor. So I plug in, I set this factor equal to 0, and I solve for x. Then I plug that into the function to check if it gives me 0, which it did. And then I said, oh, that means I can divide this function by this polynomial by this expression. It's a linear expression, but it's not in the quite of the form that we want it to be to do synthetic division. So what I did is I wrote it as a fraction. The polynomial on top and the divisor at the bottom. To get the divisor to have a coefficient of 1, I divide by the coefficient that is already there, which is 2. So I divide the numerator and denominator by 2, and I get this little expression right here. That expression is now what I'm going to be dividing. So I'm dividing the top expression, which is the polynomial divided by 2, by the bottom expression, which is the linear factor divided by 2, which gives me negative 5 over 2, which I wanted to begin with. I do synthetic division, and my remainder is x squared plus 0x minus 6. Not remainder, my quotient. My remainder is 0. So that means this polynomial, actually, this polynomial factors out to be 2 times this factor times this remainder. Because I divided top and bottom by 2, effectively I factored out 2. So the original polynomial has to be adjusted back. So that's where this modification is. And then of course, x squared minus 6 factors out to be x plus square root 6 times x minus square root 6, the difference of squares. And that's my answers. Moving on. And I know I'm running a little bit behind, so I might have to speed this up a bit. This thing is not cooperating. For some reason, this PDF has stopped cooperating with me. All right, so the next question is, for the following expressions, use the rational zeros theorem to find all real number zeros. Choose one of these for us to do. Number 21 is a choice. So selecting number 21. That is not one of the questions. You're supposed to select from number 22 to number 39. I literally just did number 21. Number 30. All right, so let's do number 30. I can only choose one of them, so let me give everyone the choice. Do you want me to do number 30 or number 39? Or we have number 36. 30, 36, or 39. Choose one. All right, 2 votes for number 39. Number 39, then we'll go. All right, it says use the rational zeros theorem to find all the possible zeros. All right. So first of all, so to find all the zeros. So first of all, if possible rational zeros. The possible rational zeros are positive or negative factors of 6. What are the factors of 6? One, 3, 2, and 6. So 1, 2, 3, 6 divided by the possible factors of 8. What are the factors of 8? 1, 2, 4, 8. So that means our rational zeros, possible rational zeros, are 1 over 1, 1 over 2, 1 over 4, 1 over 8. So it's plus or minus 1, plus or minus half, plus or minus 1/4, plus or minus 1/8. Next, 2 over 1, 2 over 2. 2 over 2 is already 1, so we already have that covered. 2 over 4 is half, that's already covered. And 2 over 8 is 1/4, that's already covered. So then the next one we try are 3. 3 over 1, plus or minus 3. 3 over 2, plus or minus 3 over 2. Plus or minus 3 over 4. And plus or minus 3 over 8. And then for 6, plus or minus 6 over 1 is, those are the 2. Plus or minus 6 over 2, which is 3. Plus or minus 6 over 4, which is 3 halves. Plus or minus 6 over 8, which is 3/4. So that's it. Those are all my possible rational zeros. Now, because there's no sign change, let's put it this way. If I do f of x equal to 8x to the 4 plus 26x cubed plus 39x squared plus 26x plus 6, f of x has no sign change. So there's no positive zeros, no positive zeros. So the possible rational zeros, we don't know about the irrational ones, are, okay, let me just quickly indicate that f of negative x, I need to show that before I go on to the possible rational zeros. F of negative x is 8x to the 4 minus 26x cubed plus 39x squared minus 26x plus 6. All right? F of negative x has 1, 2, 3, 4. 4 sign changes. So either 0, 2, or 4 negative zeros. All right, let me see what the questions that are being asked here. Is it plus or is it negative x? It's negative x. So what happens is this, and I see your question, Madison. F of x, I just call this whole expression f of x. There's literally no change in signs. They're all positive terms. Therefore, there are no positive zeros because there's zero sign change. Then I replace all my x's with negative x. When I replace this x with negative x, that still becomes a positive x to the 4. But when I replace x with negative x here, it becomes a negative x cubed. That's how I got a negative here. Replace the x with negative x, you get a positive x squared, so that doesn't change. But when I replace x with a negative x, I get a negative 26x. And then the 6 doesn't change. So how many sign changes? From positive to negative, that's 1. From negative to positive, that's 2. From positive to negative, that's 3. And from negative to positive, that's 4. So does that answer your question, Madison? All right, Hussein, I'm still not clear about what you're saying. Okay, you got it. Madison, do you understand how I got the 4 sign changes for the f of negative x? Okay, good. I see your response. Now, this tells me that since I have 4 sign changes for the f of negative x, that means I either have 4 negative zeros or an even number less. That leaves me with either 2 or 0. Either I have no negative zeros, 2 negative zeros, or 4 negative zeros. So my possible rational zeros then are now going to be negative. If I go in order, would be negative 3/8. Well, let's start from the largest. Negative 6, negative 3, negative 2, negative 3 over 2, negative 1, then what am I missing? Negative half, negative 3/8, negative quarter, negative 1/8. I left off negative 3/4, right? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one did I miss? I still left off negative 1/4. Thank you. Now, what we're going to have to do is plug in numbers and see what works. We're going to start off with the easy numbers. So which number should I try to see if it works? Negative 1. So I'm going to do f of negative 1. If negative 1 works, then x minus negative 1 is a factor. F of negative 1 is 8 times negative 1 to the 4 plus 26 times negative 1 cubed plus 39 times negative 1 squared plus 26 times negative 1 plus 6. Does that give me 0? That's 8 minus 26 plus 39 minus 26 plus 6. It's not going to give me 0 because we're adding a bunch of even numbers with an odd number. What does that give me? Answer is 1, which is not 0. So this is not a factor. All right? All right, next one. Let's try another one. F of -2. 8 times -2 to the 4 plus 26 times -2 cubed plus 39 times -2 squared plus 26 times -2 plus 6. What do we get for that one? All right, so someone says we have an answer of 30. -2. All right, so we keep checking. So what number do we try next? Let's try -3. I'm not going to put that down there, but yeah, you can fill in the appropriate blanks. $225. Which one do we try next? F of -6. Now, what does that tell you that we should probably choose? Because the whole numbers don't give us nice answers. We probably should choose -1/2. Let's try -1/2 then. What do you get when you choose -1/2? Oh, we did get 0. Thank you very much. Now that means -1/2 is a factor. What do we do with that? Sorry, not negative. X -1/2 is a factor, I should say. What do we do with that? X plus half is a factor, not -1/2, x minus -1/2. So we do some synthetic division. That is correct. Okay, so we're going to do f of x divided by x minus -1/2. So we have negative half and our coefficients 8, 26, 39, 26, and 6. And then I just drop the 8 first. Multiply 8 times negative half, I get negative 4. Negative half times 22 is negative 11, which we add to 39. What's 39 minus 11? 28 times negative half is negative 14, plus 26 is negative 12. Negative 12 times negative half is, oh, sorry, positive 12. Is negative 6. Remainder 0. So we end up with f of x is equal to x minus negative half times 8x cubed plus 22x plus 22x squared plus 28x plus 12. All right, what do we do now? What can we do now? All right, we can't factor this part that easily because it is, well, I mean, we can probably try factoring by grouping, but I don't know if that will work. In fact, I doubt it will work. Right, we can do synthetic again with what number? We're going to try what number this time. We can see if negative half works again. That is correct. So I'm going to plug in negative half into this expression and see if this works. So 8 times negative half cubed is negative 1. Well, let's work it out. I'm just not gonna kill myself over this. 8 times negative half cubed plus 22 times negative half squared plus 28 times negative half plus 12. And that doesn't work. So what number do we try? By the way, we'll try negative 3/4. Okay, so just a little side note here. Did you try negative 3/4 and see if it worked? Oh, it could take forever on a test, but let me show you something quickly that would save you some time on the test. This is why I also put the link to Geogebra, not Geogebra, to Desmos. Note carefully what I'm going to do here. I think some of you can suspect what I'm going to do. I do f of x equal to 8x to the 4 plus 26x cubed plus 39x squared. Oh, my bad. Plus 26x plus 6. And there you have it. Negative 0.5 and a negative 0.75. Do you see that? Do you all see what I just did? Zooming out. Okay, this is kind of messed up. It only has those two real number zeros. So we had 2 zeros, and then, so if you do the Desmos graph, you will see that, how do you put the exponents? To put the exponents, what you do is click on this little thing here, and there's a little, there's a square, that's an exponent button. So if I put X, and then press this button here, it's square. Oh, sorry. If I put X and then press this button here, it gives me a place for an exponent. Does that answer your question, Sheldon? Okay, great. All right, so. And then when you draw the graph, it will help you to see pretty quickly where your intercepts are. -3/4. So what we're going to do now is another synthetic division of -3, but x plus 3/4 is. So that means that there are only two, it looks like there are only two real zeros. So doing a little division again, we have -3/4. Oh, okay. Times 8, 22, 28, and 12. We drop the 8. -3/4 times 8 is -6. 22 minus 6 is 16, I believe. And then times that is -12. 24, 8 minus 12 is another 16. And that gives you -12, and that's 0. And so this becomes, f of x becomes x plus half times x minus 3/4 times, no space, people, no space. So f of x becomes x plus half from the first factoring times x plus 3/4 from the second factor times 8x squared plus 16x plus 16. By the way, if you factor out 8, you will get 8 times x plus half times x plus 3/4 times x squared plus 2x plus 2. And as you can see, this doesn't factor. If you split up this 8 into 2 times 4, you end up with 2x plus 1 times 4x plus 3. And then the x squared plus 2x plus 2. So the real zeros are -1/2, -3/4. And the complex zeros you will get from solving the quadratic formula. That's going to take a little more time. I think I should do the complex zeros. What's the question? One is what? This is not 1. You have to do a quadratic formula here. So So x is equal to -2 plus or minus the square root of 4 minus 8, which equal to -2 plus or minus 2i over 2. So the complex zeros are 1 plus or minus I. Those are my complex zeros, 1 plus or minus I. And that gives us all 4 of them. Now that was a lot of work. Which question was that? Number 39. So that's one reason I chose that one. Well, I didn't, you chose, but I was happy that you did. Gave us some extra work. All right, we are out of time with this topic. You're gonna have to review the video and do some additional practice on your own to get a handle on the rest of the stuff. I was gonna show you on Khan Academy, one of the things you can do on Khan Academy is when you're doing your exercises, your assignments, let's say you're doing a question here on you're doing a question, quadratic functions, word problems, start. What you can do is if you are stuck on a question, you could simply click on hint and get the hint there. But in addition, you can simply do something like this. Open your computer thing, scroll down. If you're at Windows 10, you can do this. If you don't, I'm not sure how it works on a Mac or on another browser or another operating system. There's a snipping tool on Windows. You can just click new and snip it. And then once you snip it, you copy that snip and paste it into a Word document or PowerPoint or whatever. And then you can send that to the tutor and say, can you help me with that? All right. The zeros for the answer that you were asking about, these are the zeros right here. There are 2 real zeros and 2 complex non-real zeros. So there are 4 in all, and there should be 4. You're correct. There should be more than 2. There are 4 in all, but not all of them are real numbers. 2 of them are complex. They are conjugates of each other. 1 plus I, 1 minus I. My bad, I messed up. That's negative 1 plus I and negative 1 minus I. Which number did I divide all equations by? Which one are you referring to? Over on the right side here? What are you referring to? To get 2x plus 1 here? All right, Madison, thank you. On a Mac, you can press Command plus 3 to get it. All right, so what I did was I took this 8 and split up into 2 numbers, 2 and 4. 2 times 4 is 8. 2 I multiplied to this expression. 4 I multiplied to this expression. Christopher says it's Shift Command 4 to copy. So, Leonard, did you get it? This 8 out here was split into 2 times this and 8 times this. I'm sorry, 4 times this. All right, so those with Macs, you can, work out the nitty-gritty of that. So that's what you can do if you need some support about a question. I think the quickest way to get help with a question is by just having Khan Academy do the hint and then just redo the exercise afterwards. If you do Command 4, you can crop your snip on a Mac. All right, I am going to move on to the next thing, which will be on the test, and that will be the rational functions. So again, I'm going to encourage you to watch the videos on rational functions because you will need to work on that. Of course, you have to watch the videos on polynomial as well because I didn't need to do a bunch more examples, but you will definitely need to watch the videos on rational functions because there's a lot here. Actually, before we start, I have to take a quick 5-minute break. So we're going to take a 5-minute break, and then we're going to talk about rational functions. So we're taking a 5-minute break here. We'll now pick up on rational functions. All right, so let's take a look at what we have here. Rational functions. Rational functions, we are going to be looking at those polynomials. A rational function is a polynomial divided by a polynomial. All right, and as long as the denominator is not 0, we're good to go. So here's an example of a rational function. To find the domain of a rational function, just find out all values of x that makes the denominator equal to 0 and throw that out. So the domain is every number except for -3, or in interval notation, -infinity to -3 parentheses, union parentheses, -3 to infinity. In this case, the domain would be everything except for -2 and +2. All right, and you can do the interval notation for that. To find the domain of this third example, you have to find the, you'll have to factor it or set denominator equal to 0 and solve for x. And of course, if you get complex number solutions, then all real numbers work. This is, there's more details in this one if you watch the video on Blackboard. So, end behavior. Because rational functions may have vertical asymptotes, you can have different ends in the function. You have what happens as you go toward negative and positive infinity. That will tell us about horizontal asymptotes. And you have also things where there's a break in between, like a domain restriction, and that could possibly give us vertical asymptotes. All right, when you have a vertical asymptote, as x approaches a particular number, they are from one side, either from the right side, that's what that plus is saying, coming from the right-hand side, or from the left-hand side, then x either goes to positive or negative infinity. So as x approaches 0 from the right-hand side here, the function goes to positive infinity. And as x approaches 0 from the left-hand side here, it also goes to positive infinity. This is a graph of 1 over x squared. As x approaches negative infinity, the graph levels off on the x-axis. And as x approaches positive infinity, our graph still levels off on the x-axis. So the x-axis is a horizontal asymptote. So we say as x approaches positive infinity, y approaches 0. As x approaches negative infinity, y approaches 0. The vertical asymptote occurs at x equal to 0. When we plug in 0, we get no answer. So it's a domain restriction. And then as x approaches 0 from the right-hand side, the graph goes upward. And as x approaches 0 from the left-hand side, the graph still goes upward. So the question is, how can we figure out vertical and horizontal asymptotes? To find vertical asymptotes, well, this is an example of the 1 over x graph. I'm going to leave you to look at the video for that one. To find vertical asymptotes, it's relatively easy. It's a little bit involved. To find vertical asymptotes, this is talking about the horizontal. I'm going to bypass that for now. And oh, by the way, you should know the graph of 1 over x, and for that matter, you should know the graph of 1 over x squared. 1 over x is the reciprocal function. And of course, the reciprocal function has the nice property of, since you should know it, you should be able to recognize the transformation. So if I have 3 plus 1 over x, that means you take the 1 over x graph and shift it upward 3 units. That's the blue graph here. All right. That means the asymptotes get shifted as well. So horizontal asymptote gets shifted upward 3 units as well. Now, how do you find the vertical asymptotes? To find the vertical asymptotes, first you find the domain restrictions. Whatever values of x don't work. So we're going to factor the denominator, set it equal to 0, and then those are my domain restrictions. But before you can jump to that conclusion that those are vertical asymptotes, you have to make sure that these numbers you get do not work, give you 0 when you plug it into the numerator. So for example, when I plug in 4 into the numerator, I don't get 0. And when I plug in -1 into the numerator, I get 1 minus 2 plus 5. That's 4. So when I plug in 4 and -1 into the numerator, I don't get 0. So for it to be a domain a vertical asymptote, it must be a domain restriction that does not give you 0 in the numerator. One of the ways to best do that is to factor the numerator and denominator after you find your domain restrictions and cancel any common factor, and then use the canceled version to find the vertical asymptotes. Now let's see what this looks like on Desmos. So I'm just going to call it R of x, just to keep it consistent here, equal to, I'm putting the numerator in parentheses, x squared plus 2x plus 5, and then divide by, which is just this division symbol here, parentheses, x squared minus 3x minus 4. And then let's see what the graph of that looks like. And as you can see, there are a couple of vertical asymptotes. One of them should be with 4. See, the graph goes toward negative infinity when you approach 4 from the left. And it comes to go up toward positive infinity when we approach 4 from the right. All right, not easy to see, but you can see it as I go along. So that's what the graph looks like. It's kind of a hard scale to hit, but you get the idea. So going back to my PowerPoint. So for vertical asymptotes, the first thing you want to do is find the domain restrictions. Then factor the numerator and denominator and simplify so that there's no common factor. Once you cancel the common factors, then you look for the denominator. Whatever makes the denominator of the simplified fraction equal to 0, that will be the indicator for your vertical asymptote. X equal to that number is your vertical asymptote. And there's a little illustration here. This is from the pre-calculus book by Blitzer. All right, these examples are done in the textbook, in the video. So I'm going to bypass them for now and talk quickly about horizontal asymptotes and then oblique asymptotes, and then spend the rest of the time doing some examples. And for horizontal asymptotes, it's what happens as you go toward the left or to the right of the function. It turns out that you will only have one horizontal asymptote for a polynomial, for a rational function. A rational function will only have one horizontal asymptote. An horizontal asymptote occurs when you go toward either positive infinity or negative infinity. It turns out to be the same number, same one, whether you're going from the left or toward the positive infinity or toward negative infinity. All right, so how do you find the horizontal asymptotes? There are three possible cases. You can either have, in a rational function, either the numerator degree is smaller than the denominator degree, or they are the same, or the numerator degree is bigger than the denominator degree. All right? Like a regular fraction, either the top is smaller than the bottom, they're the same number, or the top is bigger than the bottom. In this case, we're looking at the degree. Either the degree of the numerator is greater, or the degree of the denominator is greater, or they're the same. If the numerator denominator degree is smaller than the degree of the denominator, that means the denominator is getting bigger faster than the numerator is. And so over time, the function will get closer and closer to zero. So if you have a rational function where the degree of the numerator is smaller than the degree of the denominator, then the x-axis will be the horizontal asymptote, which means the line y equals 0 is the horizontal asymptote. The degree of the numerator here is 1, the degree of the denominator is 2, which means the horizontal asymptote is y equal to 0, which is the x-axis. The graph levels off at the x-axis. Let me show it to you on Desmos. 2x plus 5 over x squared. Um, 2x plus 5 over x squared minus 3x plus 4. As you can see, the graph levels off on the x-axis as you go to the right-hand side, and also as you go to the left-hand side. Now, it does cross the x-axis somewhere, but then it comes back up and levels off eventually. So the horizontal asymptote is the x-axis when the degree of the top is smaller than the degree of the bottom. When the degrees are the same, then the functions are leveling off, the degree of the top and the degree of the bottom are the same. Then what's happening is the functions are balancing each other out as you go toward the end. And the only term that will eventually matter would be the first terms. So therefore, as we get bigger and bigger, eventually this 5 and this 4 don't matter. And then over time, this 4x and this minus 3x don't matter. The really things that matter are the leading terms. And so you end up with 2x squared over x squared, which is 2. So the function is going to level off at 2 at the ends. So when you graph this function, the horizontal asymptote will just be the leading coefficient of the top divided by the leading coefficient of the bottom. That is if they have the same degree. Both degrees in this case is 2. When you draw the graph will level off at the y equal to 2, which is what we get when we divide 2 over 1. Okay, let me just show that to you now. 2x squared plus 4x plus 5. And the bottom is x squared minus 3x plus 4. As you can see here, let me zoom out a bit. This graph, well, zooming in, as you go to the left, the graph eventually levels off at 2. See, it's getting closer and closer to 2. Takes a while, but it eventually levels off at 2. And then if I go to the right-hand side, the graph again, levels off at 2. It doesn't mean that you can never get 2 as an answer. It just means as you get bigger and bigger, the graph eventually gets just closer and closer to 2. So that is the horizontal asymptote. Now, those are the only 2 times you'll have a horizontal asymptote. When the degree of the top is smaller than the degree of the bottom, and when the degree of the top and the degree of the bottom are the same. When the degree of the top is bigger than the degree of the bottom, then you will not get a horizontal asymptote at all. In that case, you could possibly get an oblique asymptote. If you get a horizontal asymptote, there is no oblique asymptote. If you get a horizontal asymptote, then there is no oblique asymptote. You only get an oblique asymptote if there is no horizontal asymptote. So if I ask you for asymptotes and there's an oblique and there's an horizontal asymptote, then there will not be an oblique asymptote. All right? Now in this case, how do you get an oblique asymptote? If you get the oblique asymptote if the degree of the numerator is 1 more than the degree of the denominator. So if the degree of the denominator is greater than the degree of the denominator by 1. If the degree of the denominator is 4 and the degree of the numerator is 5, then you will have an oblique asymptote. However, well, if you simplify the fraction, simplify the function. However, if the degree of the numerator is more than 1, greater than the degree of the denominator, then no oblique asymptote. It should only be greater by 1 when you simplify. So when you do the division, you end up with, how do you find the oblique asymptote? You divide the numerator by the denominator, and then the quotient will be the expression for the oblique asymptote. The quotient should be a line, a linear expression. The equation of that line, y equal to that linear expression, will be your oblique asymptote. So to find the oblique asymptote, you first must verify that the degree of the top is 1 more than the degree of the bottom. Then you do long division and then look at the quotient. We don't care about the remainder. We look at the quotient. Y equal to the quotient is the oblique asymptote. So here's the summary. Also in the textbook, the pre-calculus textbook by Blitzer. If the degree of the top is less than the degree of the bottom, then y equal to 0 is the horizontal asymptote. If the degree of the top is equal to the degree of the bottom, then y equal to the quotient of the leading coefficients is the horizontal asymptote. If the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. And if you have an oblique asymptote, what you do is you divide the numerator by the denominator. When you get a linear quotient, y equal to that linear quotient is the oblique or slant asymptote. Slant and oblique asymptotes are the same. If the degree of the top is more than 1 greater than the degree of the bottom, then there's no oblique asymptote. And there are some examples there. So to find vertical asymptotes, find all values of x such that that are not in the domain, simplify the rational expression, and cancel common factors, and then whatever is in the denominator, that's your vertical asymptote. For oblique asymptotes, you first, for horizontal asymptote, you check, as I just said, the degree of the top is less than the degree of the bottom, then the x-axis, y equal to 0 is the horizontal asymptote. If the degrees are the same, y equal to y equal to the quotient of the leading coefficients, and if the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. If there is a horizontal asymptote, then there is no oblique asymptote. If there's no horizontal asymptote, there may be an oblique asymptote if the degree of the top is 1 more than the degree of the bottom. And these examples are done in the video. I won't be covering graphing rational functions because I won't have the time. So all I'm going to do here is I'm going to recommend that you watch the video on graphing rational functions, and it will be useful for the Khan Academy videos, okay? So what I'm going to spend the rest of the time doing here is actually doing some examples. I'll be doing some examples from the textbook. And besides, you can always just graph the function on one of the graphing calculators on Desmos or Geogebra, depending. So I'm going to bypass this part here. Let me see if there's anything of interest that we need to know. Yeah, this one here. Let's say I'm graphing this function, x squared plus 4x plus 3 over x squared minus 9. The first thing you want to do is find all the domain restrictions, and the domain restrictions would be x is not equal to positive or negative 3. That's domain restrictions. That doesn't mean that we have a vertical asymptote at either of these. What you need to do now is factor both the numerator and denominator and cancel off common factors. Then when you look at the resulting simplified expression, you realize that the only place we have a vertical asymptote is x equal to 3. There's no vertical asymptote at negative 3, only at 3. So what happened at negative 3? At negative 3, the graph actually has a hole. So you plot your points, you draw your graph. It's doing all of that stuff. I'm going through all of this stuff. I'm skipping all of that stuff. Your horizontal asymptote is at 1 because the coefficient of the top is equal to the coefficient. The degree of the top is equal to the degree of the bottom. And so 1 over 1 is the horizontal asymptote. And so when you draw the graph now, you'll see the graph looks like this. It's taking a while, but now notice at negative 3, this says you should normally get negative 1 over 9. However, in the original function, negative 3 was not an option. You are not supposed to use negative 3. So when we simplified it, it would have given us negative 9. We're not allowed to use that value because it's not allowed in the original function. So where we would normally get our answer, we put a hole there. So that's what the graph looks like. Let's take a look at what the graph looks like on GeoGebra. So I'm going to go back to the original function. X squared plus 4x plus 3 over x squared minus 9. Now, if you notice here, when I plug in negative 3, it says, oh, let me zoom in a bit. When I plug in negative 3, oh, it says undefined. I'm zooming in so you can see it. Negative 3 is undefined. It doesn't show it like that on the graph. When I take it out of the graph, you don't see that it's undefined. But when I put it there, negative 3 is undefined. And then over to the right side, when we look at 3, there's a vertical asymptote at 3. Okay, sorry about that. There we go. So there's a vertical asymptote at 3. So that's what the graph looks like. All right, I gotta hurry because we're running out of time. There we go. So when you draw the graph should look something like this. It's a rough sketch, not drawn to scale. Vertical asymptote at 3, but not at negative 3, even though there's a domain restriction at both. Notice that the calculator drew the vertical asymptote, but did not show the hole in the graph. It did not draw the horizontal asymptote, but you can see where it could be y equal to 1. So that's that. All right, we're running low on time. I'm going to see if I can squeeze out an example here. So let's go to the rational functions. This is on the OpenStax textbook. I'm going down to the exercises for rational functions. All right, let's quickly take a quick look at these questions here. Choose a question from number 10 to 19 and one from 25 to 29. Let's do this quickly. Number 10 to 19. Number 17 is selected. All right, find the domain, vertical and horizontal asymptotes. Let's do that one. And then from 25 to 29, number 29 is selected. And if time allows, let's do one from numbers 30 to 34. Choose one of those, please. Number 33. Okay. Let's see if I can get this stuff set up quickly before we run out of time. First, number 17. All right, so the first thing you want to do for number 17, it says, find the domain and the vertical asymptotes and the horizontal asymptotes. So first I'm going to do this. I'm going to say, oh, look, f of x. Set the denominator equal to 0. So for the domain, we set the denominator equal to 0 and solve for x. And then we get x squared equal to 25. So x is equal to positive or negative 5. Therefore, those are not allowed to be x values because if x is equal to those values, then it doesn't work. So the domain then is everything to the left of negative 5, everything between negative 5 and 5, and everything to the right of 5. That's our domain. Any questions about that? Next, find our vertical and horizontal asymptotes. To do that, we're going to factor the expression x plus 5 over x plus 5 times x minus 5. And then I'm going to simplify that. We see that the x plus 5 cancels. We end up with 1 over x minus 5. But we have to remember the domain restriction that x is not equal to positive or negative 5. So we're remembering that. Now when we look at this then, we can see that the denominator equals 0 when x is equal to 5. So the vertical asymptote is x equal to 5. You see that the degree of the top is 0 and the degree of the bottom is 1. So since the degree of the top is less than the degree of the bottom, then the horizontal asymptote is what? That's correct. Y equals 0, the x-axis. Y equals 0. And of course, if there is a horizontal asymptote, then there is no oblique asymptote. All right, good. So that's that. Next example was number 29. For number 29, the question is find out what's the end behavior of the polynomials. All right, so let me just quickly grab this and snap this. All right, so for this question here, it says, what is the end behavior? Describe the local and end behavior of the function. So what we are gonna have to do here is simply factor whatever can be factored. So f of x is equal to 2 times x squared minus 16 over, and the bottom here is 6x squared plus two numbers that multiply to be negative 30 and add to be positive 13 are 15 and negative 2. I'm going to just do the factoring here quickly. So f of x is equal to 2 times x minus 4 times x plus 4. And you factor out 3x from this, you get 3x times x plus 5 minus, 2x times plus 5 minus 1 times 2x plus 5. So that means f of x is equal to 2 times x minus 4 times x plus 4 over 2x plus 5 times 3x minus 1. Looking at this function here, you see that the domain is that x is not equal to negative 5/2 and x is not equal to 1/3. And since there's nothing that cancels, you have vertical asymptotes. That are at x equal to negative 5/2 and x equal to 1/3. Now, those are asymptotes. What are my behavior at those points? At this point, I'm going to recommend that you draw the graph, okay? So let's see. Horizontal asymptote. The horizontal asymptote, who can tell me what the horizontal asymptote is? What if the degree of the top is bigger than the degree of the bottom? Then there is no horizontal asymptote. Okay, so I think I have an answer here. Y equal to, what is the horizontal asymptote, folks? 1/3, that is correct, because the degree of the top equal to the degree of the bottom. No, yeah, degree of top equals degree of bottom. So y equal to 2 over 6 equal to 1/3. Now that means as x goes to the left or to the right, the y value will level off at 1/3. Now, as x approaches -5 from the -5/2 from the left, the y value either goes to positive or negative infinity. As x approaches -5/2 from the right, the y value still approaches either one of those, as x approaches 1/3 from the left, or as x approaches 1/3 from the right, we also have some answers. So let's see how we get those answers. And I know we're basically out of time, but let me show it to you in GeoGebra. This is what you will need to do to get a quick response. You go into GeoGebra, you sketch a graph. 2x squared minus 32 over 6x squared plus 13x minus 5. And then when you look at the graph, you see here that as x goes toward -5/2 from the left-hand side, the graph keeps dropping. So you just say, oh, as we go toward -5/2 from the left-hand side, the graph goes downward, -infinity. But when we go toward -5/2 from the right-hand side, the graph goes upward to +infinity. So we then say that the graph goes up toward +infinity. Then when we say we go toward 1/3 from the left-hand side, the graph keeps going upward. You'll have to look at the graph to see it. And so that means as we go toward 1/3 from the left, the graph keeps going upward to +infinity. And as we go toward 1/3 from the right-hand side, and you can zoom in to see what's going on here, the graph keeps dropping. So that is my domain restriction here, infinity. So that's what they're talking about, the end behaviors on the inside. Now, our time is up. I'm going to continue recording and the lesson up until I finish doing the last example. So anyone who wants to stick around and see me doing the last example, you're welcome to do so. And the rest of you are free to move about the country, but you can look at the recording afterwards. So this question is asking, so there was a question that says, what if the degree of the top is bigger than the degree of the bottom? The same thing you will do, you will sketch the graph and see what it does as you go toward the ends. Is it rising or is it falling? So let's take a look at one of these. Number 33 was the question. So for number 33, the question says, find the slant asymptote, which is called the oblique asymptote, for the following function. So let me just save that now. And those of you who need to leave, you can leave. As I said, I'm going to have this as a recording, as part of the recording. The recording may be a little bit delayed because I have to fix an issue that came up when I was switching over. And I have to see if I can actually do that editing. So let me show you what I'm talking about with this one. If I go to Geogebra, not Geogebra, Desmos, and I sketch this graph, 6x cubed minus 5x over 3x squared plus 4. When you look at that graph, you will see, you see that the graph goes upward as you go to the right and downward as you go to the left. So you'll say as x goes toward -infinity, y goes toward -infinity. And as x goes toward +infinity, y goes toward +infinity. And as you can see, it's leveling off on a line after eventually. We don't know what the equation of that line is yet. So we know that there's no horizontal asymptote because the degree of the top is 1 more than the degree of the bottom. So what we're going to do to find the oblique asymptote, we're going to do a long division. Denominator divides into numerator. Just remember that I don't skip over any term. So any term that is not accounted for, I put 0 in space, including the constant. And then I divide. 3x squared into 6x cubed is 2x. Then I multiply 2x times 3x squared is 6x cubed. 2x times 4 is 6x. Then I subtract, not 6x, 8x, sorry. So then I subtract, and then I get 0x cubed, 0x squared minus 13x. All right, and then plus 0, of course. And then I go 3x squared into 13x is minus, let's just make sure I have this right. 2 times 4 is 8, yeah. So I get minus 13 over 3, which I then multiply 13 over 3 times, negative 13 over 3 times 3 is negative 13x. Oh, sorry, I am mistaken. My bad. My apologies. At this point, I'm stuck. Sorry. 3x squared does not go into 13x because the degree doesn't, the top doesn't work. So there's a question, rational function going to be on the test? Yes. Yes. I'm going to ask about the vertical, horizontal, and oblique asymptotes on the test. And I may also ask about the end behaviors. So 3x squared does not go into 13x, so we're stuck. And so this is going to be the remainder, but we don't care about the remainder, we care about the quotient. So the oblique asymptote or slant asymptote is y equal to 2x. Now let's take a look at our graph on Desmos. I'm going to add to that y equals to 2x. And as you can see, the graph levels off with that graph there. The two graphs level off. Eventually, they will pair up because y equal to 2x is the oblique asymptote. Okay? So that is our answer there. That's all we have time for today. Watch the video, do the Khan Academy assignments, and see what you can get done here. And this time I have to wrap up here because I have to work out a few issues. But that's all for today. You're free to move about the country. Please make sure you review the videos. Next class we'll be doing exponential and logarithmic functions. And please make sure that you watch those videos before next class. That's all for today. All the best. We won't be going over rational functions next class because that will be on the test before next class. So you might want to review the video, this video of this lesson, as well as the video on Blackboard.